Welcome back. We're going to talk today about surface integrals, and we're going to restrict our discussion to surfaces that have two sides. You might say, wait a minute, how can a surface have something other than two sides? Well, this famous example I'll put up here of a Mobius strip. If I take a strip of paper, give it a half twist like this, and then connect it, has the interesting property that it actually only has one side. You can take your handy dandy pin here, for instance, and start drawing at this point here. Let's see. And I go along. And I keep going around. Eventually I come back on the back side of where I started, and I keep going. Takes longer than I thought, but eventually I keep traveling along this strip of paper and get back to where I started. There it is. This paper only has one side. So we're not going to discuss these kind of surfaces. You can imagine why. They also have the interesting property that if you cut these, and I'll start a cut here. Unlike an ordinary ring of paper that divides into two separate rings, this strip of paper, called the Mobius strip, actually separates into one ring of half the width. And then actually, if you change this a little, and instead of giving a half twist, give a half twist and another half twist, so you give it a full twist. Now once again it becomes a two-sided paper. You can try it by drawing, and you only down the middle continually like I did on the last example. And you wind up only coloring one side. And if you cut this one, with two half twists, a full twist if you will, now it separates into two rings, but actually they're joined. You can make paper change this way. Anyway, so curious case of surfaces. We're going to stick to the one-sided surfaces today. And we'll say here is a surface integral. Right? We've done integrals over plane regions. Why can't we do an integral over a curved surface instead of a flat surface of a plane? We'll say if sigma is a surface given parametrically, so x, y, and z are all a function of two variables, you can imagine having sort of a curved object where you've, like this, you've got a u-axis and a v-axis and it runs around. And suppose it's a smooth surface, which we haven't said exactly what that is. We can actually try and find a surface integral. We'll define the surface integral of a function f of x, y, z to be, so this is the notation for it, the limit as the number of pieces goes to infinity of some k going from 1 to n of f evaluated at a point x k star, y k star, z k star on the kth piece of the surface. All right, 1, 2, 3, 4, 5, 6, 7. I can break up this into n pieces, and on the kth piece, some arbitrary piece, compute f at an arbitrary point on the surface, times delta sk, the area of the kth piece. Then I can take the limit as n goes to infinity of the function evaluated at an arbitrary point times the area. And this should look like an analogy to what we did when we were calculating, for instance, the mass of a rectangle, we took the area of the kth piece of the rectangle times some function on there, and we could get something like the mass of that rectangle, if this is the density function, by adding up the estimated mass for the little pieces if f is continuous. Similarly here, if f is the mass density on a curved surface, then this double integral over the surface will estimate the mass of the surface. And so what we need in order to make sure that this exists regardless of the choice of partition and regardless of the point we pick in the middle is to do the following. Suppose the surface is smooth and we have an orientable and we have a continuous function f defined on the surface, and then this thing will exist, and furthermore we have a nice theorem that can go with it. The double integral over the surface sigma is equal to the double integral over a plane region R in the UV plane over which you've partitioned this, right? You've partitioned, say, U going between A and B and B going between C and D or something. And you integrate f of x, evaluated at U and V. Remember that was the parametric surface, x equals x of UV, y equals y of UV, z equals z of UV. You have to write x, y, and z as functions of u and v. Take the length of dr du across dr dv dA, and that's the big theorem. Rather than going through the long, complicated proof, this really isn't used very much. It's sort of a fallback if the next theorem doesn't work. But this is the theorem, you can take a look at your book, that applies most generally to surfaces. In the special case that your surface is given by z as a function of x and y, then that theorem reduces to this one. Alright, suppose x is equal to u, y is equal to v, and z is a function of x and y, then this becomes, instead of writing u, you could, x of uv, you can just write x because x is equal to u. Instead of writing y of uv, you can just write y because y is equal to v, and z of uv becomes z of xy, and then this length of the cross product, dr du cross dr dv, turns out to be this. You can see the book and work it out. And so you just have to integrate over the region of projection r in the xy plane, since you, right now, x and y are going between a and b and c and d, say, or whatever your limits are. You can evaluate a surface integral this way. This is the only thing we're going to do, but I wanted to point out the other theorem, which is more general. You can also do this if y is a function of x and z, and you can project into the xz plane and write a similar integral, dy dx squared plus dy dz squared plus 1, integrated over the region in the other plane, other coordinate plane. All right, so there's nothing sacred about it making z a function of x and y is the point. Here's an example. Suppose I wanted to do this surface integral, our mass density or charge density or whatever it is we're trying to integrate over the surface is yz. And suppose we want to integrate over the surface that is the plane, z equals 2 minus x minus y, that lies in octant 1, right? This is x plus y plus z equals 2 if you put it in standard form for a plane. Now, in order to evaluate this integral, we need dz dx and dz dy, so we calculate over here. dz dx is minus 1, right? Derivative minus x. dz dy is derivative minus y is minus 1. And so this square root becomes square root of minus 1 squared plus minus 1 squared plus 1 squared, right? dz dx is minus 1, dz dy is minus 1. And then for f of x, y, z, you replace y, z. Well, y comes straight across, but z is equal to, it has to be written as a function of x and y, is 2 minus x minus y. So this is the integral we have to do. And then what do we integrate over? It's over the plane region, that's the projection. Well, here's the plane, goes through points 2, 2, 2. All you have to do to figure that out is go to the original equation of the plane, plug in x and y equals 0, and you get, oh, z must be 2. Plug in z and x equals 0, you get y equals 2. Plug in z and y equals 0, you get x equals 2. So you find the three intercepts here Then you notice that if that's the plane, then the projection is this little triangle that goes out to 2 and 2 on the x and y axes, so this is the region of projection. So we have to integrate over this triangle. The triangle, x goes from the minimum of 0 to maximum of 2, and it goes from the line y equals 0 to the line here, which has slope minus 1 since it goes down 2 and over 2, and goes through y-intercept 2, so this is y equals mx plus b with slope minus 1 and intercept 2 is how I got y equals 2 minus x. So we'll integrate now y going from the bottom curve, y equals 0, to the top curve, y equals 2 minus x going from its min to its max, right? This is a vertically simple region, type 1 region it's sometimes called, and we just have to integrate over that. Well, this is kind of a messy integral. The first part isn't too hard. Integral of 2y, this is partial integral with respect to y, is y squared. Of minus xy, the partial integral is minus xy squared over 2, and the partial integral of minus y squared is minus y cubed over 3. Now you got to plug in 0 and 2 minus x, and you get this horrible mess, and you realize a lot of these are pretty complicated to do. What you can do for these, I'll point out, is put them on your handy-dandy calculator rather than going to a lot of work of pouring that through. I recognize you can integrate polynomials. When you have a simple polynomial integration, here's my TI-89. Let's see, zoom it out just a bit. And on this one, let's see, it's just a little further down. You'll notice that over the 7 key is an integral sign. If you push second 7, it'll put up this integral sign. If you push second 7 again, it'll put up another integral sign. Then you type in y times parentheses, there's parentheses up here, 2 minus x minus y times square root 3, there's a square root button by pushing second square root. And then comma y, comma 0, comma 2 means integrate on the inside integral with respect to y from 0 to 2 minus, and it goes off the edge. Let me look over there real quick. Use the arrow key to go across. That's okay, wait a minute. Oh, there we go. Didn't go far enough. Okay, y goes from 0 to 2 minus x. Close the parentheses for the inside integral, and then comma x means the second one integrate with respect to x, comma 0, comma 2 parentheses. So the second integral on the outside integrates with respect to x from 0 to 2. When you push enter, it puts up, you already see I tried this before, but I'll push it again. It puts up a max line, and now it comes up again. The pretty print version of your integral, and you can check if it looks alright. Integral 0 to 2, 0 to 2 minus x y times 2 minus x minus y square root 3 dy dx. And you can do these double integrals on your calculator, and this says it's 2 square root 3 over 3, so I trust it. And I find I always make mistakes when I try and do these long, complicated things, even for simple polynomials. So there's the answer. The first problem is 2 square root 3 over 3. Now let's try another problem. Some of these problems you need to switch coordinate systems, for instance. Here's one. Suppose I wanted to do the surface integral of x squared plus y squared times z over the portion of a sphere that's over the plane z equals 1. The sphere x squared plus y squared plus z squared equals 4 of radius 2, right? Well, let's see. Here I drew a picture. It always helps to draw the picture to figure out what you're doing. You realize that the projection down here is going to be a disk, and it's going to have the radius of this intersection of the sphere with the plane at z equals 1. So you set z equals 1 in this equation, and you get x squared plus y squared plus 1 squared equals 4. This is the intersection curve here. Or x squared plus y squared equals 3. Evidently, this boundary, the boundary of the intersection is a circle of radius square root 3 centered at x and y equals 0. And so the projection down here is this disk of radius square root 3. Alright, so when I write the surface integral and apply the theorem, I have to do the double integral over the disk of radius 3, this plane region. The function x squared plus y squared times z gets replaced with its equivalent. Well, from this equation, solve for z is the square root of 4 minus x squared minus y squared. So x squared plus y squared z, solved from the equation, and then square root of dz dx squared plus dz dy squared plus 1 dA. Pretty complicated, these surface integrals. So this is why you need your calculator. Even if it can't do them analytically like that, your calculator can get you a number estimate for these things if you're over, put in specific numbers on these. Now to evaluate this integral, I have to evaluate dz dx. Well, it's a little harder. I solve this for z, and I get z equals this square root, and if I take the partial derivative with respect to x, I get this, minus x over square root of 4 minus x squared minus y squared. You can do that on the calculator too, but you should do this one by hand. Dz dy, similar to minus y over square root of 4 minus x squared minus y squared. So here's dz dx squared plus dz dy squared plus 1 put in. All times this stuff. What a mess. I can't possibly do that. This is where you need the other coordinate system. Switch to polar coordinates. This is r squared, 4 minus r squared, square root. And then this becomes x squared plus y squared is r squared on top over the bottom squared is, when you square it, is 4 minus r squared. So these two added together give this term, and then plus 1 hanging on the end. And dA is r dr d theta since it's polar coordinates. Now I've got an easy integral I can do. Let's see, it's just integral r squared times, well, if I multiply this square root into here, these two cancel and I get r squared. This one in here becomes 4 minus r squared, and now the r squareds cancel, and I just got integral r squared times r is r cubed, and then, the square root of 4 is 2. And now I just have this simple integral to do. Well, it splits into the product of two integrals, integral from 0 to 2 pi d theta, integral from 0 to square root of 3r cubed, and wind up with a simple result, 9 pi for this surface integral. All right. Finally, just a few closing comments on this section. Try some of these. This is all there is really to it. You just need to, on each of these surface integrals, draw the picture to give you a little hint. Be able to calculate those partial derivatives, dz dx and dz dy. Choose an appropriate coordinate system, and integrate over the region of projection in the xy plane. Here's a few applications. For instance, the centroid of a surface. Interesting thing about the centroid, unlike the lamina that's flat, where the centroid tends to come out on the lamina, unless maybe you got a ring and it comes out between it. This thing tends not to come out on the surface itself, so the centroid doesn't tend to be on the surface, but nonetheless you can calculate a centroid for the surface, the curved surface, and you can also use this surface integral to calculate flux in physics. We're going to be looking at this in upcoming sections here. This is an important quantity, the amount of the volume of a fluid or something flowing through a surface per unit time can be calculated with the surface integral. Also, if you have a curved surface with charge on it, you can integrate the charge density and get the charge, or if you've got a curved surface with a mass density, you can integrate that mass density to get the mass of the surface. So those are some of the interesting applications why we study these things. Try the homework.